In this video, we're going to talk about chemo-mechanical coupled processes. And before we get started, I'd like to divide these two into chemoplasticity and chemo-elasticity. In chemoplasticity, we deal with problems in which inelastic deformations are caused or assisted by chemical process. For example, you could have dissolution of minerals that could help a rock to lose porosity and get more compacted, or in some other cases, you could have the dissolution of a mineral helping to a fracture to propagate. This is an example, which is shown, for example, in this paper over here, in which we did a study of how dissolution of a mineral at the tip of the fracture would help the propagation of that fracture with the same pressure, with the same stress conditions, but just with a change of toughness at the tip of the fracture. So basically the idea here is that the acid leak-off decreases the strength of the rock, and that helps the fracture to propagate. And of course, this is an inelastic process and goes into the category of chemoplasticity. We'll not talk in detail about this type of problem because plasticity is something that we're going to see in later videos. So in this talk, we'll just talk about chemo-elasticity, in which we have recoverable strains. And the extension to what we have seen so far, it's more or less straightforward. We're going to update our constitutive equation, in which the first thing that we saw was to relate stress to strains through the stiffness matrix. Then we saw that if we had fluid in the pore space, we needed to update this equation to incorporate the deformation caused by the pressure of the fluid with the BL coefficient. And later we added also the component of thermoelasticity, in which the stresses are also going to be a function of changes of temperature. All right, now we're going to add one more term, which is related to changes in the chemical potential of the solid or the fluid, and we're going to assume, to make it easy for this case, that these changes of chemical potential, where the chemical potential is mu, we're going to assume that the changes cause only volumetric strains or normal stresses. So that's why, similar to the case before, as for thermoelasticity, we just have a bulk modulus here, and here we have an identity matrix. And this parameter gamma is just a coefficient or a parameter similar to the ones that we see over here, like beta and alpha. It's just one more parameter that characterizes this equation. So in general, now with this equation, we can take into account several types of actions on the same porous solid. This part, as we said, is the mechanical part. This second part is the poroelastic part, or also sometimes called the hydrological part, because the presence of a fluid, many times in geoscience, is water. And this is the thermal part, and last we have the chemical part. Solving this problem altogether is something that is not easy, but it can be done, and it's actually very important to many problems in not only in geoscience but also in material science. In geoscience, these are what are called the Thermo, hydro, chemo-mechanical coupled processes. Or usually they just go by the acronym THCM. Something very interesting of these chemical-mechanical coupled processes is that when you combine two physics that you didn't have before, you sometimes have phenomena that would not occur otherwise. For example, the case of thermoelasticity is a good one. We have seen that if we have a solid and we do not let it expand, then we have a thermal stress. Something that would not happen if we did not have that condition of not allowing the solid to expand. So here, in that case, in the case of thermal stress, we're combining the thermal part and the mechanical part. And with a combination of those two, I see something that I wouldn't have if I just consider mechanics or if I just consider thermal. And sometimes you can combine two or more of these physical processes, and sometimes the four of them, and get to phenomena that you wouldn't see otherwise if you had the actions just by themselves. And this is something which is called emergent phenomena. And these processes are important because they are the result of the combination of different physics that combine in order to produce something that you wouldn't see otherwise. Okay, so for understanding a little bit better these examples of chemo-elasticity, we're going to see two examples in a little bit more of detail. The first example, it's an example which is related to the swelling of clays with the change of the chemistry in the pore fluid. And usually this is referred to as the chemical sensitivity of clay rocks. And we know that shales are rocks that many times are composed by a majority of clays. In this case, what we have is a phenomenon which is due to the interaction between the pore fluid and the clay within the rock. A clay rock or a mud rock or a shale has as a building component clay platelets. They are very tiny. They go from 1 micrometer for the case of, for example, kaolinite, to almost a thickness of 1 nanometer for montmorillonite. And these very tiny platelets, although they might see that they are right next to each other and touching each other everywhere, like for example, like grains of sand would do, or a continuum matrix of a carbonate would do. In the case of the mud rocks, this is not the case, especially if they have a high porosity. If you were to zoom in into looking at the clays, you will see that these mud rocks are composed by clay platelets that have one dimension which is much shorter than the other. So if we do a cross section, they look, let me put this one a little bit further. They look like these rectangular shapes that I'm drawing. And not only that, they have the shape, but they are usually negatively charged because of the oxygen atoms on the surface of the clay. The fact that they are negatively charged is responsible for the water molecules to orient with the hydrogen atoms. This is the oxygen, and these are the hydrogen, and the hydrogen it's here positively charged, so that this positive charge tends to align or tend to be attracted by the negatively charged surfaces. So this is the oxygen again. And here now we have water in between these platelets. And not only water, but many times in geological applications, the water is not by itself. We don't have distilled water in rocks. What we do have are solutions of water with salts, where those salts are ions. And for example, if we had a sodium chloride salt, what you will have are ions, cations of sodium that would also tend to stick closer to the negatively charged surfaces in order to cancel the polarity of such surface. So this is going to be the sodium, and let me find another color here to draw. We also are going to have in solution the chlorine. So the distance between this platelet is a function of how much I can cancel the polarity of the clay platelet with my distributed ions in the brine solution. And we see that that distance between platelets, d, is a function of the ionic concentration of the brine. And when you have more cations that stick to the clay and polarize and neutralize the polarity of the surface, then the distance between the platelets tends to be smaller, and when the ionic concentration decreases, the distance between the platelets tends to be higher. This is due to electrical repulsion between the atoms that make up the clays and are also distributed in the brine solution. And sometimes this is also known, especially for relatively low ionic concentrations, as a double layer theory. Okay, so ionic concentration is basically the amount of salts that you have in the brine. And for example, if you were to freshen the water within the pore space, that would be a process in which you go from a high ionic concentration to a low ionic concentration. And that happens, for example, when you are drilling a wellbore and you are using an aqueous base or a water-based drilling mud. For example, let's make here, let me do this, I think that's fine. Let's imagine that we have a sand formation, a shale formation, and again a sand. And we're going to drill a wellbore through those formations. And as a result of doing the wellbore, in order to drill this wellbore, I'm going to need a drilling mud in order to keep the wellbore stable. And that drilling mud is going to have a composition. Let me try to finish here making this schematic, and we'll go into looking at what is the effect of the composition of the wellbore mud on the chemistry of the shale. Okay, so if I am drilling this wellbore, and let me just make this, I'm going to take advantage to make a nice drawing this time about this process. So here we have the drilling string, and here we have the drilling bit, which is making the wellbore. And of course this one is rotating. And okay, now let's talk about the drilling mud. The drilling mud is going to be composed by, let me do it with another color. It's going to be composed by water if we're doing a water, if we're using a water-based mud, and that mud is going to infiltrate into the formations as we drill through the formations. So if we have a very permeable formation, then the filtrate of the water of drilling mud is going to get further into the formation, as for example if we have a shale. But it's going to infiltrate a little bit more as well. All right, so what happens in this case is that if we are using a low salinity water-based mud, the water which is contained within the drilling mud is going to permeate into the formation and is going to mix with the brine within the shale. Both the sand and the shale are originally brine saturated, and usually this salinity tends to be high, and therefore if I'm using a solution with a low salinity and lowering the salinity of the water within the pore space of the shale, the result is going to be that the ionic concentration is going to go from a high concentration to a low concentration. Actually, I just see that my arrow here was let me think again this. So we are going to from a high concentration to a lower concentration, then we're going in this direction. Yes. And this is where what we're doing when we freshen the brine. And in that case, as you can see, if the ionic concentration decreases, then the distance between the platelets is going to increase as well. And the result of that is going to be that if I have a process like this, I'm going to have a process of swelling of the shale rock, because the distance between the platelets is going to change. And this process is going to cause additional hoop stresses in the case in which the rock is not allowed to expand in the tangential direction. And this is actually the case over here, right? So if we, from here, if we make a cross section of the wellbore, this is a cross section. If, for example, we had our hoop stresses in this region that were concentrating and producing more compression at these two locations, with the decrease in the ionic concentration of the water as the rock tries to swell, but it can't because there is more rock around, the result is going to be that the hoop stress is going to increase. And if the hoop stress, if the hoop stress gets larger than the compressive strength of the rock in triaxial conditions or the shear strength, what I'm going to have as a result is a breakout. So, for example, if I had a small breakout with without the chemical action, now with the chemical action, I might have an increased breakout zone because the increased hoop stresses due to the action of the shale swelling but not being allowed to swell. And not only that, but sometimes the swelling can also cause the weakening of the rock itself. So it's not only that the hoop stresses increase, but also the rock is going to get weaker. Okay, so I have a few examples to share with you about this phenomenon of swelling. And let me go over here. So in this video, we see basically an animation of what I just explained before, that when the water interacts with clays, it produces an expansion of the distance between clays. This is the case in which you have a very small distance between the clays even without water before. And I'm going to come back to this in a minute. This is it's a cartoonish type of animation of this phenomenon. Let me bring a video over here that shows that, but based on molecular dynamic simulations. So here what we see, let me actually run it from the end to beginning. Here we have clay platelets modeled through molecular dynamics. And also we have the ions, which are the blue spheres, and we cannot see the water. The water has been made invisible in this case, and it is in between the platelets and in between the ions. And let me go, this is the paper and the reference of that video, but what you really have in that simulation, it's a lot of water molecules and some ions in there and the clay platelets. And what we see in this video is that when the ionic concentration is high, then the distance between the platelets is short. However, when the ionic concentration decreases, like, let me play the video, the distance changes. So I'm playing backwards the video, which is kind of simulating an expansion, but the opposite will happen if you have a contraction and if the ionic concentration is increasing instead of decreasing. I like this video very much because it also shows how the platelets start to align as the porosity decreases. And I have one more example related to clay swelling in this case, and this one is in this video, in which we see two types of sediments. One, it has more a higher fraction of sand, and the other one has a higher fraction of clay. And these two are subjected to water imbibition. So as water imbibition occurs, you see how this other sediment starts to swell. And it swells because the clay is swelling. and the clay swelling as a response of the equilibrium distance between the clay platelets that we discussed before. And this taken into the wellbore environment can cause this phenomenon that we talked before, and actually can cause many times drilling stability problems. So we're not going to see in detail the equations for this case, but let me talk about the solutions. How would you solve this problem in order to avoid that swelling and the weakening of the rock by freshening the pore water? Well, we cannot control the rock and we cannot control what it is in there originally, but we can control the composition of the drilling mud. And for example, if we were using a water-based mud, the solution would be to increase the salinity of the fluid in the mud. And this is what is done in this animation that we were taking a look at before. That, for example, a very standard salt to use in drilling fluid is KCl, potassium chloride, that it would prevent the swelling. Such salt, if it has a salinity which is equal or higher than the salinity of the resident brine, then it's not going to cause a drilling stability problem. The other solution is just to use something else than water. And that's what you do when you use an oil-based mud. In this case, what you do is just to replace the water by oil, and oil, it's a non-polar fluid, and it doesn't hydrate the salts, it doesn't break the salts, and it doesn't create ions, and it doesn't create the phenomenon that we see in this case with brine. And one more solution, a little bit more mechanical than chemical, is to try to mitigate this leak-off. The problem here is that some fluid is getting into the shale and it's mixing with the resident fluid and it's causing that freshening of the pore water or the pore brine. So if you, instead of having what we see in this figure, which is a leak off from the wellbore into the formation, if you want to have the opposite flow from the formation into the wellbore, what you need to do is to drill with a mud that causes a pressure which is lower than the pressure in the formation. And this is what is called underbalanced drilling, in which the pressure in the mud, in the drilling mud, is smaller than the pore pressure in the formation. In that way, what you would do is to produce a flow that goes from the shale into the wellbore, so that the fluids are going into the other direction. Of course, you have some diffusion, but it's not going to be as bad as the case before, in which you do have this advection and the flow got the brine getting into the shale. Okay, this is one example of chemical interactions, and particularly for shales, due to the change of the chemistry in the pore water. And we saw how that links to mechanics through this expansion term. Let's see now another example of chemo-elasticity. And this example number 2, it's an example which is called adsorption-induced deformation. And it's something that most of you have faced already in your regular day-to-day life. What happens when relative humidity increases in the air? And of course, we're talking about water. Your hair is going to change shape. At very low relative humidity, the hair tends to stay straight. But as relative humidity increases, water molecules start to cling onto the hair and cause it to bend. And if you have a relative high humidity, and if you have more or less curly hair, this is what is going to happen. And this phenomenon is caused by the absorption or preferential attachment of fluid molecules, water molecules, onto surfaces, solid surfaces. And let me show one other example that it's pretty nice and show this phenomenon very well. Okay, so let me come back here to my browser, and this is a video I wanted to share with you. In this case, what we see is what is called a high-grow bot. High-grow comes from humidity, relative humidity, and what we're going to see, it's a solid that it is designed in such a way that the changes in relative humidity that are being varied in cycles cause this solid to move. There is no motor in here, there is no nothing. It's just the change of relative humidity that makes these solids to bend and respond to that action. So what I want you to remember from this video is that processes of absorption can cause solids to change shape and to swell. And this is actually something that also has an application in geoscience. And let me come back here to my OneNote. It turns out that organic matter, it's a type of a solid that tends to change shape and tends to deform with absorption of fluids that we find in the subsurface. So let's say that I have a pore or a solid which is completely made of organic matter. I have fluids like, for example, in order of more sorbing to less sorbing, CO2, methane, and nitrogen, that when exposed and when present in this pore, in the pores of these kind of materials, they tend to attach and look preferentially for the surface. That's a more stable configuration than being on the middle of the pore. And on the middle of the pore, you find it in what is called the bulk phase, what you predict, for example, with an equation of state, but you're going to find a lot more molecules on the surfaces, on what is called the adsorbed density, which is higher than the bulk phase most times. And what this is going to cause is something similar to what we see here on the top, is that the presence of these molecules in sorbent state are going to cause what is called a surface stress. And it's going to cause what we see on the top, it's going to cause a deformation. And because it's caused by this phenomenon of absorption, we call it adsorption-induced deformation. And in the case of organic matter, what this is going to produce, let me just draw it again without the molecules in there, just to make it a little bit clearer. If this is my pore and I have a process of uptake or sorption, the solid is going to change size and it's going to get bigger. So let me summarize this. An increase of the absorption amount is going to cause in organic matter an increase of volume. Okay, so let's see how we can analyze this a little bit more rigorously, and how can implement this phenomenon into reservoir geomechanics. The first thing that we're going to do is going to be to quantify this amount of sorption. And this is usually done through what is called a Langmuir isotherm. If you have a surface and you have absorbed molecules into it, as we were saying before, close to the surface, you will have a high density. And as you go into the bulk, you will have the bulk density. So in this case, we could calculate and measure the density of that fluid phase, and it's going to depend on the distance from the surface. It is going to be the highest next to the surface, and it's going to tend to the bulk conditions as you get further away from the surface. Whatever is in here, which is in excess of the density of bulk conditions, is what is called excess sorption. And usually we refer to it with the letter N. And since it is excess, we add there the EX. And if you do measurements of this excess sorption, what you tend to see is that the amount of excess sorption is a function of the pressure of the fluid. The higher the pressure of the fluid, the higher the sorption amount, and it's a nonlinear relationship where the excess sorption depends through the Langmuir parameters NL and PL, which are fitting parameters, and it is proportional to pressure. This is what is called a Langmuir isotherm, and models pretty well the amount of excess sorption that you have in this type of materials. For example, in organic shales, the amount of excess sorption increases with the amount of organic matter and decreases with temperature. Okay, but let's try to incorporate what we postulated before, that increase of sorption would cause an increase in the volumetric strain. All right, so let me add the pressure axis over here, and usually what we see is that also with the increase of pressure, we tend to see that the deformation, volumetric deformation induced by absorption also looks more or less like the Langmuir isotherm. And for this Langmuir isotherm, I could also define this volumetric strain caused by absorption as a function of the Langmuir type isotherm, but here now we will have epsilon L pressure, and this Langmuir pressure may or not be exactly the same. But at the end of the day, what I see in this type of media is that now putting this together is that the amount of absorption-induced volumetric strain is usually linearly proportional to the amount of absorption, where in a process of adsorption, I would go into higher amount of, let me do this with another color. A process of absorption would imply higher amount of sorbed fluid, and a process of desorption would imply a decrease in the amount of sorbed fluid. A process of desorption is what would happen, for example, with reservoir depletion. Why? Because we are lowering the pressure in reservoir depletion, so that causes desorption. So let me add the arrow here for desorption, because that's what we're going to study now. Desorption will go this way. And desorption now would cause a shrinkage of the organic matter, because we're going into this direction to lower volumetric strain. Okay, let's now add this component to pore elasticity. Let me just write the equation. You can verify that in some papers that I have published. This is going to be the pore elastic part at the beginning that we already know. And now there's going to be an additional term which depends on something that we call the absorption stress. And this adsorption stress is a function of pressure. In this case, I'm going to assume that the absorption stress is the same in all directions. So I'm just going to keep it as here in scalar, and this is going to be times the identity matrix. All right, this absorption stress is what now is also going to contribute to changes of stresses. And it's going to work very similar to what we saw for thermoelasticity, in which, for example, a sorption process will cause dilation, and if constrained, will cause more compression. A desorption would produce, if constrained, less compressive stresses, or sometimes even tension. And a real application for this equation is what happens in cold bed methane. Cold beds are a type of geological formations, but especially cold bed methane, or I would say unminable coal beds are those coal beds which are too deep to be mined. So instead of being mined because they are too deep, something else that you can do is to extract the methane out of those. So let's draw this coal bed at some depth. Usually these coal beds are naturally fractured so that they have a high permeability uh, even without doing any hydraulic fracturing. So you can just put the well in there, and many times just by decreasing the pressure in the wellbore, you're going to have an economic production rate. All right, so let's place a wellbore in this case and into this unminable coal seam, and we're going to depressurize this wellbore in order to produce gas out of this formation. What we're going to do is, as we have done before, we're going to assume that the vertical stress is constant, and we are going to draw to lower the pore pressure so that we produce a fluid, and in this case we actually produce a methane. Let me add just one more detail in here. So these things are natural fractures that in the world of cold they are called cleats. Okay, this is going to be a depletion problem, and we're going to add the absorption component, and we're going to also add another component, which is the fracture permeability. The fracture permeability is going to be included and is going to be added to our problem to what is called a fracture compressibility. Basically, when you have a fractured rock, let me make a schematic of a fractured rock over here. The conductivity of the fractures in this fracture medium is going to be proportional to the width of the fractures, where the width of the fracture, here let's call it H, is here, and the spacing between the fractures is S. We're going to call it S. For fracture porous media, and assuming a flow, a laminar flow, you can calculate that the fracture of that, the permeability of that fracture media is going to be proportional to the cube of the thickness of the fractures divided 12 times the spacing between the fractures. And empirically, you can also show that the higher the effective stress on this medium, the lower is going to be the spacing between the fractures, and therefore the lower is going to be the permeability. And usually these plots are done in terms of the logarithm of permeability with stress, and the logarithm of permeability decreases more or less linearly with stress. In this case, we're going to refer also, and we're going to be interested mostly on the horizontal stress. And in this case, let me add here the title. This is effective horizontal stress. Okay, so I think we are almost ready to get started with solving our problem. Let me see if I forget something. Um, no, I don't think so. All right, so we're going to solve graphically this equation that we have over here. And if you haven't seen the depletion lecture, I would recommend that you do that. And I'm also post a link about the drain solution just for pore elasticity, but now we're adding the chemical component. All right, let's apply a pressure drawdown. This is going to be pressure or borehole pressure, BHP, and as a function of time, we are going to lower this pore pressure from here, let's say, to there. And we're going to keep this pressure linear for some time. What do you think is going to happen with stresses? If you remember the solution for the drain problem, stresses would vary as follow. This is also time. And let me add here a marker. Okay. Well, let me actually extend this a little bit more. I realized this was too short. All right. All right, now we're ready. First of all, what's going to happen to total stress? Total stress, as we have seen, we're going to have the vertical stress and the horizontal stress. And we're assuming in this case that the total vertical stress is going to remain constant. So for example, if SV was at this value of the pore pressure in the formation, then after some time it's going to be the same. The overburden is not going to change. And even when I go quite far in time, this is not going to change. This is going to be the value of SV. What is going to happen to the horizontal stress? The horizontal stress, we have seen that the drain solution for a pore elastic medium implies that the total horizontal stress is going to decrease as the pore pressure decreases. And let's say, for example, that we were in normal faulting and that horizontal stress starts somewhere over here, and because of the decrease in pore pressure, the total horizontal stress is going to change as well. This would be the case for a reservoir without experiencing any absorption-induced deformation. What would happen in the case of let's finish with a solution for the case without absorption. So let me actually write this in here. This is a solution without absorption induced deformation. That let me put an acronym for this, just for the following plots. We have seen also that according to the pore elastic solution, the effective stresses in this case are going to change. For example, the effective horizontal stress, sigma h, as a function of time. If you remember that solution, we said that the effective horizontal stress without absorption-induced deformation would increase. And this was caused by the Poisson ratio. So this is without absorption-induced deformation. And one more thing, what would happen now to permeability in the horizontal direction as a function of time? If the horizontal effective stress increases according to this law that I have over here, the permeability of the medium should, if the effective horizontal stress increases, then the permeability should decrease, right? So increased effective horizontal stresses are going to cause the permeability, let's say the initial value somewhere over here, is going to cause this permeability to decrease. This is what you would expect in a fracture formation. In all types of fracture formations, this is what you see. As you deplete, the effective stresses increase and permeability decreases and the flow rate decreases with time without the presence of absorption-induced deformation. Let's now add the component of adsorption. And for the case of adsorption, as we said, when we have a depletion or a desorption process, we are going to have a decrease in the volume of the solid or the volume of the rock, or a contraction of the rock matrix. That's going to be the path of depletion. So if we have such a phenomenon in this case, when I lower the pressure in the formation, what I'm going to see is that due to the effect of the absorption-induced deformation, when I lower the pressure, the rock is going to try to expand due to the all right, sorry about that. Working from home and just had a call. Okay, what we were seeing is that this is the response for a fractured reservoir without the presence of absorption-induced deformation. However, when we do have absorption-induced deformation, as I lower the pressure, I'm going to have a process of shrinkage of the matrix. That shrinkage of the matrix in all directions, but especially in the horizontal direction, is going to cause a relaxation of the stress because I'm going to have a uniaxial strain condition. This is similar to what happens with temperature. I lower the temperature, I cause a stress relaxation. And in this case, it's going to happen something very similar, but caused by the phenomenon of desorption of the fluid and shrinkage-induced desorption. So as a result, what I see in this case is that horizontal stress is going also to decrease, but it's going to decrease more than the case without the absorption-induced deformation. And this is going to be the expected response with the phenomenon of absorption-induced deformation. What's going to happen to the effective horizontal stresses? The effective horizontal stresses sometimes could be less than what you predict without absorption-induced deformation, but sometimes may also go in the other direction and end up to be lower than they were before. And this phenomenon again is caused by the shrinkage of the matrix of the rock matrix as fluid desorbs from it. And what will happen to permeability? If I have now a lower effective horizontal stress than what I had before, that means that my permeability is going to be higher. And in this case, this is going to be my response. And this is something very interesting because it is very, very unusual in reservoir geomechanics that you deplete the reservoir and the permeability increases. And you can see this type of phenomenon in the field. And let me make a schematic about this. It usually looks more or less like this. If you have permeability and here you have time, the result of depleting some of these cold bed reservoirs is that your permeability as you start the depletion would go up. The permeability would increase. Let me use KEH just to make sure that everywhere I mean that this is a horizontal permeability. But you could wonder now, would permeability increase forever? And you may expect that the answer is no, but let's see why. You can explain this from the point of view or by using and looking at the stress path in terms of the Mohr circle. Let's draw the Mohr circle at the beginning over here at time 0. At time 0, let's say that we have a state of stress, effective stresses, which is here, where this is the effective vertical stress and this is the effective horizontal stress. And as I deplete the reservoir, as we have seen before, we would expect this Mohr circle to move to the right. Lower pressure, higher effective stresses, and if I were just to follow the apex of this Mohr circle, this one would tend to move in this direction. This is a depletion stress path. But now let's consider what happened in this case. In this case, my effective horizontal stress is not increasing, it's decreasing. And not only that, but my effective vertical stress is increasing because I'm lowering the pore pressure. The shrinkage of the matrix is not changing the effective vertical stress. The effective vertical stress is going to be the same that you expect with the depletion path. So let me add the Mohr circle for the depletion stress path so it's clear. So for the depletion stress path, then I would expect a Mohr circle, which is somewhere over here. But now with the desorption, I have a decrease of the effective horizontal stress. So my new effective horizontal stress with the shrinkage of the matrix is going to be here. And the effective vertical stress is going to be somewhere over there. So my new Mohr circle now is going to be here. And if my Mohr circle is large enough and it gets close enough to the shear failure limit, the rock is going to fail in shear. So this minimum horizontal stress cannot decrease forever. This permeability is not going to increase forever. This is going to happen when the thickness, the width of the fractures increases. But when I get to the point of shear failure, what is going to happen is that the rock is going to start to fail and probably at the beginning you may have some dilation, and the permeability may increase more. Actually, it's going to increase very quickly at the beginning, but then as the rock fails and fines start to get produced between the fractures, this permeability is going to drop. And sometimes it may go up and it may drop again, but it's going to get very unstable after the shear failure process. Why? Because we have hit the shear failure line at which the reservoir rock is going to start to fail. And this process that I drew here, it actually happens in reservoirs, and it actually happens in this type of applications of called bed methane. So just to finish, let me clarify here that the Mohr circle, actually, let me do this for the depletion. This is going to be now the component of the desorption stress path that causes a Mohr circle to increase in diameter. And let me just clarify a few things over here just to complete this example. So in this region, we have fracture width increasing. In this region, we have fracture dilation. And in this region, we have fines production, which clog the fractures and lower the permeability. All right, so I wanted to share this example because it is an example that it's very relevant to reservoir geomechanics and to coupled chemo-mechanical processes.